Well, guys, if there is no other question, I go to the next participant, which is Lennart. Lennart Benschop. We will present floating point transcendental functions.
Okay, so we're now on we are doing floating point on the Agon computer. We have we start this. We are now on an emulator. Do you see the share screen now?
Perfect.
Yes.
Yes. We load Fort 24. It's not. So first of all, Agon is a easy 80 based machine, which means it's an 8-bit. It's based on a Z80, but it has an extended address bus, and it has a faster core. And one of the things, it can run in Z80 mode, so it runs all the classic Z80 code, or including CPM, or it can run in an ADL mode, that's the long address and data mode, and then the original 16-bit registers are extended to 24 bits, like HL is in fact a 24-bit register. You have 24-bit adds, you have 24-bit index registers. So in fact, you're kind of working with a 24-bit machine, and I wrote a Fort on it where indeed the cell size equals 3 bytes. That's very unusual. And yes, I can. I have 24-bit integers like -1 u. That's 16 million. That is 2 to the power 24 minus 1. Indeed, the words are 24 bits. We do have double precision numbers, so these can be quite large. And since a while we have floating point on these, so we can like 3e, that's the floating point number 3, and we can use a square root of these and print that one. That all works. So where did we go? I wanted to have floating point support on that Fort, and originally I thought, well, we have the C cross compiler environment that's called agdev. I left the C runtime library. I left the floating point function from it, but these were copyright Zilog. I wasn't very comfortable that these are unencumbered to use. They're properly taken from the ZDS cross compiler environment. Didn't know their copyright status, and they were only single precision, and they weren't very accurate at that. They weren't doing all the good stuff that makes IEEE 7454 work as accurate as it can get in 24 bits. It's very complex standard, very complex to implement. I found out later that it's very complex indeed to implement properly. But I settled for the moment at a 64-bit format with 48 bits of precision, 15 bits of exponent, and 1 sign bit. and not the implicit leading bit, which say, so we're having fewer bits of precision compared to what regular IEEE 754 double precision is doing, but we're double the precision of single precision. So we're in that sense we're double precision still. I started view what will we f-store, for instance. So I started with a floating point stack where's our stack? That is the floating point, the f stack, that's a create, and then stack depth floats a lot, and then we have a floating point stack. We just create a memory space and put some numbers there. Each floating point number is 8 bytes. So we see that float plus equals 8 plus, floats equals times 8, but I made that a machine code primitive. A top-up stack is normally in DE. I swap it to HL, then I do 3 times the add HL HL. That is, well, 3 times adding a number to itself is shift left by 3 bits. It's times 8, and then we swap it back into DE. And then next is an inline macro that fetches the next instruction and executes it. It's the DNR interpreter inline. Now we have some things like stack manipulation. The stack pointer, the floating point stack pointer, is in a variable called FP. So that's, and now we do an F drop. We fetch the floating point stack pointer, subtract 8, and then yeah, load 8 minus 8 into BC, add it to HL, and then store it back. That's simple. Fdub, fdupe needs to copy the data. We now, what we do in most of the floating point primitives, we are using IY as a temporarily we save the IY register and we use it as the floating point stack index register to address data on the floating point stack. So we load IY from the FP variable, push it first, load it from the FP variable. At the end, we store the updated IY register back into the FP variable, and we pop the original value. The original value, normally it's used as the instruction pointer, so I have to make sure to push and pop it for each code that uses it. These are not very interesting yet. These are not very floating pointy. Store and floating point literals. And then we have some high level for it where it's like floating f comma, we store it here and we do an 8 a lot. Create a floating point variable, a constant, do the literal thing. And now we have a this is more complex than it needs to be. I think you have the floating point equals 0. Well, how the floating point numbers are laid out in memory, we will show in a moment, is how they are laid out in memory. It's like first we have 2 bytes for the sign in the exponent. So if we have, and then we have 6 bytes for the mantissa. So if we have the number 1, we create a variable fa, and now we have we store the value 1 into fa, and now we dump. We have now, we see the 00440, that's the value that the exponent has for the value 1. Then we have 1, 2, 3, 4, 5, 6 bytes, and the last one is 80. That gives a mantissa with a leading 1 bit and all other bits 0. If we have number 2, for example, and we dump that, we see 4001, so the exponent is 1 higher, and the mantissa is the same. And for 4, you can guess what we will get here. We want to, so 4. And now we see that the exponent byte increased by 1, and the mantissa is still the same. If we do, for instance, we can do half, or no, like 3. 3, we see the same value as we had for 2 for the exponent, but now the mantissa has 2 leading bits, so it's 1, 1, and the rest 0. That's the value 3, left normalized in the mantissa. And we can have, of course, a 1.5, for instance, or, well, 0.5. Then we see that the mantissa dropped, is now 3 FFF. We can do a negative, yeah, let's do a negative 1. And now we see that that there's now a BF. So the leading bit of the exponent, half 16, the leading bit of the exponent is now set. That means the sign bit is set, it's negative, and we store sign magnitude. That's how these values are represented. And then I wrote all the primitives like add, subtract. Add and subtract are one function. But I wrote all the and multiply and divide, I wrote them in assembler, and higher level stuff like to convert between decimal and binary, I wrote in Ford. So we can get back to the F plus. That's the addition subroutine. First, we order the numbers. We want to have the numbers R1 and R2. We want the number with the greatest absolute value at the R1 position, and the number with the smaller absolute value, we want to store it at the R2 position. So that's that subroutine. There's a subroutine order Fs that does that. It's quite a lot of code here. Yeah, that's the order Fs routine. It's just a normal subroutine that does exponent compare and the mantissa compare and swapping. If we need to swap them, there are other support subroutines for the add routine, but we cannot dwell on them in detail. Then we will be here by the end of today. Now, what we now do is check for yeah. What do we here? Too long. So we do a check that we're not overflow, that we are not already at the top value that the exponent can have, because then that means infinity. We just keep it infinity. We don't wrap around to some nonsensical value. And then we do the align routine. The align routine is basically what it's doing. It's shifting the second operand right until it matches the exponent of the larger operand. So suppose we have values 4 and 1. Now 4 has a 2 higher exponent than 1, and then we shift one number 2 positions to the right, so they now have equal exponents, and we can add or subtract them. Now, if the signs are equal, we do an actual addition, and the addition could overflow, and if it overflows, we shift the whole stuff to the right. We do use some guard digits, so in most cases we are using 7 bytes instead of 6 to store our numbers. We have if we have different signs, then we do the subtract. But if we have subtract, we could subtract. We already know that the top number exceeds the bottom number, so we don't get a negative result. We do get a, we cannot overflow, but the result can be less or even much less than the original number. You can subtract 2 nearly equal numbers, and if they we need to renormalize the number, shift it left until it's the leading bit is set again, and then of course decrease the exponent accordingly. And then we do a rounding. Rounding in itself could overflow. It could overflow from say the all f value, f 6 bytes full of f's into a 1 0 0 0. So if that occurs, we have to shift that to increase the exponent 1 and store that 1 0 0 0 thing there. Now that's a whole lot of code for the addition. Subtraction is only f negate f plus. You're following? Can still follow? Yeah. And now we have some compare routines. Oh, yeah, these f min and f max, I implemented them just in the naive way. I didn't. There are some specs in IEEE 745 that you have 754 that if you have a 1 nan and 1 valid number, you have to pick the valid number for f min and f max. That's all Now we have multiply. That's also a lot of code. It's far from optimal. And I think with this level of, with this amount of code, I could have done a full double precision instead of what I did now. That's hindsight. Maybe I'll do that one day. And then there's the code for multiplication. There are some we add basically the exponent bytes. We have some cases where we underflow and we produce a zero result. We have some cases where we overflow and produce an infinite result. And when that's all sorted out, we finally can do the real multiplication. And it's calling a subroutine multiple times. It's far from efficient. It's already lots of code. The easy 80 does in fact have a multiply instruction. The MLTBC, it's this one. It multiplies 2 bytes, giving a 16-bit result. So one byte is in B, 1 byte is in C, then you multiply and then the 16-bit result is in BC. And you have that same multiply instruction for HL, for DE also, even for SP, but that makes no sense. Really, it makes no sense. But yeah, that's just how the instructions were decoded. So that's how multiply is doing, and then we can have to, oh, that we are already into the division. We have to do a normalize and a round. Now we have some stuff for the divide. It's shorter because, well, we cannot really, we are in a loop that we are repeatedly doing trial subtractions and restoring and whatnot, and we do a rotate left of the number of the quotient bit, and yeah, there's a lot of code here, also normalized and rounding. And these are the 4 main operations. These are all in assembly. Now we have the convert double number to float. Convert double number to float. You store the number in the mantissa and you if the number is double to float, yeah, unsigned double to float, we do some checks. So if we're 0, we just store 0. If we're not 0, we do a loop. We store the number and we shift the number left until the most significant bit hits 1. It's like the normalized function. We could have shared the code with the normalized function of the addition. And we have the reverse operation that we want to convert a float number to a double precision integer. If it's too big, we just return all f's. If it's 0, we return 0. And how did we do all this? Yes, if we're too big, we return an all F number, like that's the largest number we can return. Now we have the signed versions of these. We do some manipulations of the signs, do an absolute, convert the absolute number, put the sign back on, the other way around, check the sign of the float to double, check the sign of the float number, do an absolute value, negate if it was negative, convert the, and then if we are a signed number, we use 08000 as the overflow value. So the maximum negative number we use as the overflow value. And now we bring in some constants. We even have a half already. Now we now we're getting into the high level code. Maybe I have to stop close to here. The way I debugged it was first, of course, the stack manipulation, fetch store code, that infrastructure. That wasn't doing any actual number manipulation to see if that was any good. And the first real functions I tested was the double to float and float to double functions, because I could convert a number, which I demonstrated just before going into this editor. I just showed you, well, I store number 1 in a variable, dump it, see if it makes any sense, the bits. I did that. And then, of course, I can do so we can do like 2 double precision, convert to float, and then see if that is the expected value, and it is. And what we can also do is convert it back to double and see if we get the correct value back. So I debugged those functions that way. And when these made sense, these functions, we could, we didn't have floating point number input function. It wasn't hooked up into the interpreter yet. And so but that way I could already do some things. I could create floating point numbers, do trivial additions, like and then F plus, and then see if we convert it back to this. So we could convert the double number 2 to a float, the double number 3 to a float, add them, convert it back to a double integer, and see if the number made any sense. And of course we can do a multiply as well. And that way, gradually I implemented and tested much of the add subtract functions. And yeah, if you multiply, divide, when you have divide, you can and then we have the to float routine. We have this integer power, raise a float to an integer power. It's always nice to have. We do a check the least significant bit of the exponent, and while there's still bits inside it, we multiply if it's set, and then we do a squaring of the number. So this is fairly forward implementation of an integer raised to an integer power. Now we have the to float routine. It's all written in Fort. It has some probably not well factored. You can make it much more well factored, but it's parsing the number, it's converting the number to float as you go. Well, when it's seeing numbers, it's multiplying the number by 10 and adding the floating point, the digit as a float, and it's doing the exponent, and then it's raising 10 to the power of the thing, and that's all done here. Where you have, that's done here. If the exponent is positive, you raise 10 to the power and multiply by it. If it's negative, you raise 10 to the negative power and divide by it, and you add in the sign, and now all done here. Now this is a bit of a trick function. It's checking if the word that you're trying to parse contains the letter E, and if the base equals 10, because the f number exec is a function that I define in the float in this source file, and I hook to a vector. The Fort interpreter checks if this f number vector is set to non-zero. If it's set to non-zero, it tries to execute this function, and it can parse, from then on, it can parse floating point numbers. So I don't have to do any floating point support in the cross-compiled, meta-compiled interpreter. I can hook it up later when I run the extension, when I'm just extending the Fort system from within the Fort system itself without having to cross-compile. Now, there are some functions to manipulate the exponent and to basically to scale and to so I can scale the number by a power of 2. That's very handy in the Chordec algorithm for the transcendental functions, but now we get to the represent function. That's also a big chunk of code with some corner cases inside. It's basically converting a floating point number to a string of digits plus a sign plus an exponent. So we can later in the FS routine just do some checks and check the sign. Well, we do the represent. We check the sign. We print a minus sign if we have it. We check for if it's a valid number. Otherwise, we print int. We don't really distinguish int and len at the moment. And then we print a string of digits. We print the exponent, and we print with an e. We emit the e, and we print the exponent. And that's all there is to it. We have an f dot even. It's a bit more complex, but it's printing most of the time without an e notation, without scientific notation. f.s, that's the dot s, but it prints the contents of the stack. It iterates over the stack. We can just fetch the f depth, and then the f0, f. So we can in the contents of the stack. Well, indeed, but I think we do some exercises with floor and with truncation, and even we want to round to even. So there's some tricks here involved, but I think I already spent my time. Are there questions? So we load the graphics library. And now I have two sine curve functions. This one is slow. It uses floats. This one is faster, and it uses an integer sine function. We can just look at it. The sine curve, the normal sine curve function, iterates in a loop. It converts the I to first to double, and then to float, and then to radians, and it does a sine, and then multiplies by 300, and then converts it back to an integer and adds to it for the y coordinate, and then it does a line tool. Here we do the same thing with an integer sign. We have to divide by 55 to get the same, roughly the same scaling. So the integer sign is returning numbers in the range 16,000 to minus 16,000. But the integer sign is taking degrees. It's just a table lookup, and then some, exploiting the symmetries and doing modulo 360 and exploiting the symmetries of the sine function to get all 360 degrees for a table of only so. And you see that the integer sign, which I used in the graphics demo that's included with Ford for quite a long time, it's the integer sign is quite a bit faster. That's how the integer sign works. We have a sine table from 0 to, and then it's doing all four quadrants. It's doing its thing, like flipping the x and subtracting it from 90 or from 180 and negating the number and all that stuff, and then cosine, and that's much more efficient to do it that way. We haven't even looked at floating point sine code. I think I already spent my time for this, and we should postpone the transcendental functions for the next episode. What do you think?
Perfect. Let's do that so we can show the rest of the meeting, the other participants.
So I'll stop sharing right now. Are there questions? I take that as a no. Was it interesting?
Absolutely, Lennart. Excellent.
Mind-boggling.
Okay.
Yeah, very interesting.
Yeah.
Sure, sure.
Good. Are there any questions? Guys, here's your chance. Good. If